name is Alex Gore, and I am giving a presentation on principal component analysis. So the first question is, what is principal component analysis? Well, it's essentially taking eigenvalues and eigenvectors of a data set and breaking it into principal components. This allows for easier understanding of the data, and it makes very large data sets. You can shrink them down and make them much more manageable and readable. And it also shows trends in data, and the best part, it's really easy to do. So there's a few things we need to know beforehand. The first one is variance. So we just took some data set. This is from something in the mathematical textbook that we use. Variance is essentially the sum of each point in a data set minus its mean quantity squared over the total amount of points that there are. You can also just use a computer program. We use R in class a lot, so you can just use that and plug that in, and we found the variance to be 91 point whatever. The next important one is covariance. For this, you need two separate variables. I set them like this just because it's, in order to make them actually fit on the screen, they had to be two columns. But the covariance is essentially, it's very similar to variance, except instead of squaring that quantity on the top, you're separating it into a point in the x area minus its mean times a point in the y area minus its mean. And I showed the long way of doing it down here, and then I also showed that you can just, once again, plug it into the computer program, covariance right there, really easy. The last thing is linear algebra. I can't get into how to find eigenvalues and eigenvectors mathematically, because that's like a whole lesson on its own. That would be 20 minutes. 30 minutes, you know? But so I just kind of showed the actual process using a computer. Here's just a sample matrix. I just kind of came up with this one, and here's our eigenvalues. And then each of those columns correspond with their with one of those eigenvalues. So the eigenvalue 2 here, that corresponds with this first column, and then the second eigenvalue corresponds with the second one. Also important to note is that this isn't always the case, but in this case it is something you want to do, is make sure each of those eigenvectors are the length of 1. What I mean by that is if you were to set it up kind of like a triangle, it would be a squared plus b squared. So a squared plus b squared is c squared. In this case, I just kind of showed square root of each of those squared is 1. So now we get into the actual process of principal component analysis, or PCA. I used another example from the textbook that we use. This is, the context is important when you're looking at PCA, so that you can actually understand what the reasoning behind all of it is and what the end result is supposed to be. So here we took, its scores, there's 10 students here, and then each of them had their mathematics achievements test recorded, and then their calculus grade at the end of the year. And you can see here's the graph of it. Now, we look at that graph and we don't really understand a whole lot about it. I mean, we can see, you know, this person on the top, okay, they're above average. They're good in both the test and calculus. And this person on the bottom, I guess they're probably below average because they're way down on the bottom. But all of those people in between there, what's that supposed to mean, you know? Are they above average, below average, whatever? So PCA will allow us to find that. The first step is to gather and then adjust the data. So we will take our data set that we had there, and then we're going to find the mean of each of those columns and then subtract it from each of those points. That basically shifts all the data over so that their total mean is 0, and that will just make it so much easier for us to continue with this further on. The next step is to find the covariance matrix. So the covariance matrix is just on the diagonals. It's essentially just each of the covariances involved in the possible data set. So the diagonal will be the covariance of a data point or of a column in itself, which is also coincidentally just the variance, so it saves on a lot of computation time. And then we have the covariance of x and y and the covariance of y and x. If you had more data sets, if you had like x, y, and z, it would be like covariance of x and x, covariance of x and y, and then covariance of y and z, or of x and z, and then y and x, y and y, y and z, then, you know, whatever, continuing on with that. It can be however large your data set is. The other important thing to note is that it's symmetrical across the diagonal, so covariance of x and y is the exact same thing as the covariance of y and x. So after we found that, and this is the covariance matrix of the actual data set that we had, after we find that, Step 3 is to find the eigenvalues and then eigenvectors of the covariance matrix. So here we have, these are the eigenvalues, and then their associated eigenvectors. It's also important to put these in order of the largest eigenvalue to the smallest eigenvalue, and of course their eigenvectors with them. The largest eigenvalue will be called the principal component. That means that has the most significance or just the greatest effect on all of the data. And it's definitely the most important one. When you have very large data sets, it's especially important to have that principal component recognized. The next most significant will just be the second principal component. In this data set, it's not super important, but in very large data sets, there's an optional step of removing the less significant eigenvalues and eigenvectors. This is essentially how you can take big data sets and shrink them down into small amounts, because what we're doing here is we're looking for the trends in data. And if you have, this giant 18-dimensional thing, it's going to be really hard to look at the trends. So it's an optional step. In this case, we're not going to do it because it's just 2-dimensional, so there's no reason to, but you can. Step 4 is then to multiply the original adjusted data by the eigenvector matrix. So you're going to take, since it's matrix multiplication, you have to do it in a specific order, otherwise it completely messes up. You have to take the original adjusted data, so the data that, when we took the original data and subtracted the mean, you take that on the left and then you multiply it by the eigenvector matrix, which we found earlier, and then you will get this this thing. It looks like a big mess and it still doesn't really help us, but when we plot it, it changes very much how important it is. So I put lines at x equals 0 and y equals 0 just to make it easier to kind of understand. But if you look at this data, it's essentially, we took that, that big line of stuff of all these data points, and we shifted it, or we rotated it and then shifted it over to the origin. So let's take a closer look at this. So in the context of what we were looking at, we can see those students that are in that first quadrant, this means that they are above average in both calculus and their mathematics achievements test. If you look in the fourth quadrant, those students are below average in calculus and below average in their mathematics achievements test. And then in the second, this is the third quadrant, and then the second and the fourth quadrant, they have their own things where they're below average in one and above average in the other. And essentially what this can help with is it'll allow a teacher to kind of look at students and see, okay, this student needs more help with this subject, or this student, like this one right here, they just need help with everything. Their math is really not doing well. But a student that's in this first quadrant right up there, they don't need any help. They can go on their own thing. I mean, of course, the teacher still has to help everyone, but they don't need to focus so much on explaining things to them. That student's gonna understand it. This student that's down here, they'll understand the other concepts that are on the mathematics achievements test, but not so much the calculus stuff, so they're gonna need a little extra help. So what are some other applications? Because this can be used in a very wide variety of places. It's been used in finance. There are patterns in stars and star systems where you have hundreds of dimensions. Neuroscience, where you need to be really exact, and of course, my personal favorite, baseball statistics, and many more different possible options. In very large data sets, you're really going to want to get rid of those less significant components, because as you saw when we showed it in a graph, a 2-dimensional graph, it became a lot easier to understand and comprehend. But if you keep it in that really big amount, it's kind of harder to realize what it's supposed to say. So, in conclusion, PCA, it makes data analysis easier and easier to understand. It's very, very quick to compute. It just takes a few simple steps in some computation program, and really almost any computation program works. I listed Excel, R, and Maple. Those are 3 ones that I know work in it. Any other computation program can do it well, as long as you can create matrices. There are also some other methods to doing it, some that are slightly more exact, I guess. You can use a correlation matrix. I didn't really get super in-depth into this because it's a bit more complicated, but it's a fairly similar process. So thank you for listening to my presentation on principal component analysis.
would you choose for the data set that you use to use PCA instead of linear regression?
Linear regression could work too. As far as I know, they're both kind of their own different ways of looking at it. The problem with linear regression, of course, is that I guess it's a little less exact, you know, because you would create this line. I mean, it would be a good indicator of like kind of average placement of people, but it's principal component analysis. I mean, when you look at something like this, here's a better look at this, it's a little easier to kind of understand each individual point rather than everything as a whole.
Did you look into how to decide when to, if you have higher dimensional problems, how to ignore the lesser components?
It doesn't, from what I saw, there wasn't really an exact time when it was, like this was the cutoff where you start cutting off things, but the way that I look at it, it seems like it'd be most beneficial when, if you have something greater than 3 dimensions, you're probably going to want to cut stuff off so that you can see it graphically. Yeah, exactly. I mean, you don't really need to because you can still see the differences between trends, but it's a lot easier when you can graph it.
Any other questions? Thank you again.